Welcome back to Bio 6612. Today I'm going to cover other link functions for binary data, and this is a bit of a longer lecture. I'm going to talk about the Probit link as well as the clog link and some data situations that motivate the use of those links. And then there are a couple of readings here. I think the Agresti stuff is pretty good for the Probit and clog stuff, and this is a nice sort of applied explanation for the difference between logistic and Probit regression. So far we have looked at modeling binary and binomial data using the logistic regression model, which assumes that for each subject, the probability of success, or yi equals 1, is related to a vector of explanatory variables that we call x through the logit function. So that's the model written out here. Sometimes you'll see this as 1 minus p probability yi equals 1 given x, but it's the same thing. And our focus has been on estimation and inference about beta. The estimation is done via maximum likelihood, and inference is using asymptotic results like the Wald test and the likelihood ratio test. So before logistic regression was popular, sort of what motivated these types of models is this dose response problem. And in these models, we are interested in evaluating the effect of dose on a specific event. So in these models, there's usually a single covariate, which is dose, which we can call di. The outcome is still binary. Yi is 0 or 1, and the probability that we're interested in is then the probability that yi equals 1 given di. And I'm going to just call this pi throughout this lecture today. So based on what we've seen so far to model this probability, we would use the logit link. And I just want to show you that there are other possibilities that are sometimes more appropriate. And in fact, and this is kind of neat, any cumulative distribution function can serve as a link for binary response data. So link functions for binary response data have a couple things that they need to be. One is that they should be continuous. They also need to be monotone increasing. And they should map values from the full continuous range of negative infinity to infinity to the probability range of 0 to 1. And in our general terminology from GLMs that we learned at the beginning of the semester, the link function is G. That's something that we wrap around this pi to make it compatible with our x transpose beta, which is our beta 0 plus beta 1x plus beta 2x2 plus on and on. And the even more general form of that, well, what is probability? The probability of y equals 1 given x is actually, so that's actually from the expectation of y given x for binary data is the probability. So our most general form of a model in the GLM sense is the linking the expectation of y given x to our linear predictor x transpose beta. So we want a link function that maps our expectation to the range of values the variable can take. In this case, x transpose beta, we always assume can be in the real range of negative infinity to infinity, and the expectation of y, that what's inside of this link function, that range is going to depend on what distribution you're assuming. And for binary data, that's going to take the range of 0 to 1. So we want link functions that map 0, 1 to infinity. So the common options are the logit link, which you've seen before. Also, probit link is another common one, which is the inverse normal CDF, and we write that as that link function as capital phi inverse of pi, where phi, capital Phi is the CDF of the standard normal distribution. And a third choice is the complementary log-log link, which looks like this. You take the negative log of 1 minus the probability, and then you take the log of that. And these are all models that serve to give us ways of estimating betas for data that's binary. So this is what these link functions actually look like. So if you take on values from 0 to 1, the probabilities, this is what your link, your outcome will take, the values your outcome will take. So where you have the logit link down here, and I'll talk a little bit more about this type of plot later in the context of data, and it will be a little bit clearer. But all of these have a sort of sigmoidal shape where they're not linear on the probability scale. They have some sort of like S shape. So tolerance distributions gets us back to the dose response modeling. And with these, we might want to describe the distribution in response values to increased levels of a dose. Take, for example, an insecticide study where a chemical was applied at a set of known concentrations to a batch of insects. At low doses, there are few, if any, deaths, and at high doses, most or all of them die. This is like that bloodworm example we've seen a couple times. And so there will actually be a distribution of tolerance levels to that poison dose in the insect population. And insects with tolerance of less than some dose DI for that individual insect will die when that dose level is administered, but won't if anything less than that is administered. So then let U be a random variable associated with the tolerance distribution, and little u be the tolerance for a given individual. Then the density of U is, well, that should be UI, is for a given individual. Then the density of U is F of U, which is kind of funny. So the probability of death when exposed to dose DI is just the actual integral of that PDF f of U, little f of U, which is given by integrating from negative infinity to DI the PDF. So that's actually the CDF here. So the probability of is given by the cumulative distribution function of U. So let's make this a little bit more specific and look at this in terms of the normal distribution. So let's assume that tolerance for the chemical follows a normal distribution such that U U is normally distributed with some mean and variance. So then from the previous slide, the probability for a given individual's dose causing death is the cumulative distribution function for that dose. And so I said that the CDF of the standard normal distribution is often given by this capital phi. So that's what that is here. This is a standard normal CDF for dose DI. And the standard normal, and we can replace that with our actual modeling statement, beta 0 plus beta 1 DI. Then if you, so then that implies that, so then if you actually take the inverse of that to get the actual GLM version of the model that we've seen before, what you end up with is, so take the inverse to solve for this beta 0 plus beta 1 di term to stand alone on its own. What you get is the phi inverse of the probability for a given dose, an individual, is beta 0 plus beta 1 di. And you saw that in the previous slide. This is actually just the Probit regression model where this phi inverse is the Probit link. And that comes from assuming that you have a normal underlying distribution for the tolerance of the poison. So what is this capital phi thing? What is the Probit link? I said that the Probit link comes from the inverse of the CDF of the standard normal distribution, and we call the Probit link so we call the Probit link phi inverse, and we call we call the actual CDF of the normal distribution, we call that phi. Why don't we just write it out? Like for the logit, we might write out that what that actually is equal to, which is log of p over 1 minus p. Well, the reason that it's usually written as this phi in the case of talking about the CDF or phi inverse when you're talking about the actual Probit link, that's because it doesn't really have a nice form like the logit link does. So the standard normal PDF, so let's say that y has a standard normal distribution. You can write out the PDF of that. That's going to be like 1 over 2 pi square root of 2 pi sigma or something times e to the negative y squared over 2, roughly that. So then the standard normal PDF can be written phi of y, and you get the CDF by integrating from integrating up to y the actual CDF. Sorry, let me say that again. So you get the you have the CDF here. Okay, and that's the PDF. You get the CDF by integrating the PDF. And all I really want to point out with this is not a simple equation in terms of y. So, and then for the Probit link, we actually want to take the inverse of this, which is going to be that's like a big ugly expression. So that's why we don't write it out as a logit. It just doesn't have like a nice closed form in terms of the variable of interest. And if you were to have logit, if you wanted the probit of p, so basically the probit of p is going to be this in terms of p instead of y. So you're going to have the probit link, so phi inverse of p is the integral from negative infinity to p e to the 1 over square root of 2 pi e to the negative t squared over 2 dt, and then take the inverse of that. So I'm never going to ask you to do any like calculations with this actual form. I just wanted you to show you what it looks like and where it's coming from. So what about using the logistic distribution for tolerance? So in the previous examples, or a couple slides, I showed you using the normal distribution for tolerance, which leads to the Probit link and Probit regression. The logistic distribution is an actual distribution that you can put on your data that's similar to the normal distribution. They're both symmetric about 0. The logistic distribution has heavier tails than the normal distribution, however. And so the PDF is given here. You can see the logistic in red and the normal in blue. Logistic looks similar, but it's just sort of flattened out. And then the CDFs are given here. So the logistic CDF is written out. You can write it out like this. And this might look really familiar to you because if you assume the logistic tolerance distribution for your data, then this actually leads to a logistic regression model for PI. You see, this looks exactly like the inverse logit link for if you have a model of logit, PI equals X beta, then we end up with that when we take the inverse logit to get PI in terms of X beta. So it's neat. So this just goes to show you, and you can actually use any CDF of a distribution to model binary data. I'm showing you a couple of the most popular ones. So I'm going to go through an example and this is a typical example of a bioassay experiment. And bioassay experiments are what sort of Probit models were originally developed for. In this example, we're interested in the relationship between the proportion of mice dying of pneumonia and a dose of protective, the relationship between the proportion of mice dying of pneumonia and the dose of protective serum. And there are mice with pneumonia, 40 in each dose group, who were delivered 1 of 5 possible doses of the serum. And the number of deaths were recorded. So here I have some code putting that into R. We're going to have a variable dose, which gives you the different dose levels. 1, 2, 3, 4, 5 doses we have here. The number of deaths that were recorded in each dose group. And so these are actually decreasing as dose increases. That's because it's a medicine that's supposed to help mice with pneumonia. The number of mice that were in each original group, which is 40 in all of the groups, and then the proportion that died we can calculate from the number of deaths divided by the number of mice in each group. And as an aside, one of the assumptions of logistic regression is that the relationship between the X, in this case dose, and the logit probability of Y equals 1, in this case the probability that the mouse died, is linear. So I actually calculated the logit of the proportion of the mice who died and plotted that against dose. And it's not a perfectly linear relationship here. And if you actually take the log of dose, it's a more linear relationship. So I'm going to model log dose as a covariate instead of dose because it better fits those assumptions for logistic regression. And that's something that you can always check on for your logistic regression model. So we're going to model the proportion of mice killed as a function of log dose using both a logit and a Probit link. So the logistic model, the model with the logit link, is written here. Here I'm using the cbind with the number of successes and number of failures format, because that's the way that the data is structured. I'm plotting that against, I'm modeling that against log dose. Here I'm using the logit link, though I don't have to put, I could have just gotten rid of this part of the code. That's not necessarily necessary in this case because the logit is the default. And then I'm also going to run a Probit regression model, and the only difference in the code here is that I say link equals Probit. So the results of these two models are printed in this table down here, where I have the intercept as well as the term for dose, which is, I treated dose as a continuous coefficient, so you just get one estimate value, as well as the p-value confidence intervals, the AIC, and the actual model. So the AIC is there's just one AIC per model, so we can just focus in on the bottom part here for the AIC. So the estimates are rather different. You can see that is the case for both the intercept here and for the coefficients, but that's sort of not unexpected because we're using a different link function, so the coefficient values really aren't necessarily going to mean the same thing. However, we can see that the p-values are quite, maybe not exactly the same, but they have the same, they're both very, very small for both of these coefficients, suggesting the same conclusion from a hypothesis test that dose and mouth death are associated. That would be this hypothesis test. Same for both models. We can't compare them formally because the models are not nested. So if you have a different link function, even if you have the same covariates in two models, if you have a link function, the models that is different across the models, they are not considered nested models. The AIC is slightly higher for the Probit model. I wrote Logit here, but that's not true. It's actually higher for the Probit model. And lower AICs are technically considered better. So I guess by that criteria, the Logit model is better, but this is not a large enough difference to really say that. I'd say based on AIC, these models are pretty much comparable. So you would really just make a choice based on how you want to interpret the model rather than based on the model fit here. And so what do these fits actually look like for our data? Well, here I have the data plotted, and in red is the Probit fit, and in the blue dotted line we see the Logit fit to that data. And these are nearly identical, so that gives you a good sense of why the likelihoods and the AICs are so similar for these models, because the fits are really quite similar. As I alluded to a couple slides ago, the difference really is in how you interpret the parameters rather than anything different from that. And so the Logit link we've talked about before, the parameter estimates are log odds ratios, which some people, you might think that's hard to interpret, but then the Probit link really is a lot harder. So we would say that the log odds ratios are nicer for interpretation. You cannot interpret parameter estimates using the Probit link as log odds ratios. Rather, the way that you interpret these are the coefficients for Probit models are the difference in z-scores associated with each 1 unit difference in the predictor variable. Another way is to calculate the predicted probabilities at different values of DI, and then use these to look at what dose corresponds to PI is equal to 0.05, and I'm going to talk about that in the next slide, but you can actually do that for both models. So this is really the main interpretation for a Probit model. I find that to be very unintuitive, and I think a lot of other people do as well, which is why Logit models have really sort of become the most popular. But when these type of regression models for binary data were originally developed, Probit models were used widely for bioassay type data. So one way that you can choose to interpret these models other than log odds ratios, and you can use this for the logit or the probit function, link function, is that is as using the median effective dose. And median effective dose, termed ED50, is the dose at which 50% of individuals experience a response equal to 1. For the logit link, the way you calculate this, you plug in p equals 0.5 to your model. And you can actually, and the way and then your ED is going to be your negative beta 0 divided by beta 1. And it's actually the same for the probit link since they're both centered at 0. Since for this particular model we used log dose, then ED50 is actually going to be calculated by e to the negative beta 0 over beta 1. But if you're not using log dose, you're just using dose as a covariate, then it would be this here. And using either the logit link or the probit link, we see similar results. We have both about 0.066 in the logit case or 0.0067 in the probit case. So up until now, we've only considered symmetric link functions for binary response models. Both logit and probit links are symmetric. And when I say that they're symmetric about 0.5. What I mean is you can show this equality here. But another way of thinking about this is you can tell a symmetric distribution by looking at its PDF. And in the case of using these as link functions, this means that the response curve for the probability that y equals 1 given xi has a symmetric appearance about the point where pi equals 0.5. Meaning that the probability approaches 0 at the same rate it approaches 1. And so this is sort of an implicit assumption that you're making when you choose a logistic or a probit link. And in cases where that's violated, these links are inappropriate to use. So this leads us to an alternative motivation for link functions for binary response models. Let's suppose that instead of a tolerance distribution, we have some latent continuous variable that we'll call z. Okay, when that happens, that follows some distribution f with mean eta, such that the probability of z is less than z, which we've been calling pi. No, that's not right. Sorry, scratch that. The probability of z is less than z equals f of z minus eta. Instead of observing z directly, we are only able to observe y as an indicator that z is greater than 0. So y is equal to 1 if z is greater than 0, and y is equal to 0 if z is not greater than 0. And then y has a Bernoulli distribution with a mean based on the probability that z is greater than 0, which you can calculate from the cumulative CDF, the cumulative distribution function of z. And we did some problems like this back in homework 1. So we can use a binary GLM with the link function f inverse, for where f is the CDF of z, to model the dichotomized data. So if the distribution of z is symmetric about 0, then that leads us to, then we have this sort of property here. And the link function will look like this. However, if we don't have a symmetric distribution, then the link function is not going to reduce as nicely, and you'll have something that looks like this. So if we have binary data that arises from a dichotomized latent variable, we can hypothetically use a symmetric or a non-symmetric link. It just matters what the data looks like. However, often in that case, we might think to use a complementary log-log link. That is a popular choice in this setting, in the non-symmetric setting. And I'm going to go through what that looks like. And you're going to use it in your homework, so it'll be good to know. So this link function is the inverse CDF of the Gumbel extreme value distribution. And this distribution has CDF, which I'm writing in terms of dose DI to be consistent with notation for the dose response curves above, though generally when you write probability distributions, you write them in terms of f of x or f of y. I'm just looking at f of d. So in this case, our CDF, which is also our probability that we're interested in our modeling, is 1 minus this term here, the exponent, the negative exponent of your linear predictor term, and then exponentiating that, and 1 minus that. And this corresponds to the link function that is written below. You might ask where that comes from. So in the GLM framework, we're interested in modeling G, some link function, of PI equals xi transpose beta. In this case, it's G of PI equals beta 0 plus beta 1 times dose I. And first we're starting with PI is equal to f of di from the previous slide. So, and in this case, f is the CDF of the extreme value distribution. And that's actually written out on this slide for us here. So to figure out what the link function is, the G, we just want to solve for this term here, what is called the linear predictor. So we want to isolate that. And the first thing that we'll do is say one minus PI equals e to the negative e to the beta 0 plus beta 1 di. Then we can take the log to get and you divide by negative 1. And take the log again. to get beta 0 plus beta 1 di on the right side, and this whole term on the left side, and that's what you saw in the previous slide. And so that's how you get your link function. And this is called the cumulative log link. Or maybe it's not called it's called the sorry, it's called the, it's written right here. It's called the complementary log link, not the cumulative log link. And it's called that because you have the complement of your normal probability, 1 minus your probability, and then you take the log of that twice. So just this plot looks at the CDFs, also just the link function for the C-log, when you have the C-log link or a logistic link or a Probit link. And note that that you're not symmetric for C-log link at the tails. And what that means is if you, for example, look at the Probit link in blue here, you have the same behavior as the probability goes to 0 as you do as the probability goes to 1. It sort of flattens out for a while in both cases. And that's also true for the logistic link. However, the C-log link has a different behavior at 0 and 1. At 1, at probability of 1, it behaves more like the Probit link. You can see that they sort of overlap as it gets closer to 1 here. But at the probability of 0, it behaves more like the logistic link. So I'm going to show you an example of binary data that can arise from this type of dichotomized latent variable. So when the number of infective organisms in a solution cannot be measured directly, dilution assays can be used to estimate this number. In this type of assay, a solution containing the unknown number of organisms is diluted progressively, and samples are taken at each stage and deposited on a plate containing a growth medium. For each plate, we can only tell if there is growth or no growth. We don't know that latent number of infective organisms. So the number of infective organisms is a latent variable. Growth or no growth is the observed variable. Observed binary variable. So let's suppose also that the dilution is in powers of 2. You have full strength, half strength, quarter strength, etc. And N is the number of organisms per unit volume in the original solution. Then the corresponding number at the ith dilution should be N over 2I. You can again assume that the random sampling leads to a Poisson distribution with mean mu for the number of organisms extracted at the ith step. So at the ith dilution, you'll have total, the original number divided by 2 to the ith power is the number of organisms. And the log of mu equals the log of n minus I log of 2, and I just get that from replacing this with mu and taking the log. Then the probability of no organisms at step I, so is equal to e to the negative mu to the I, and this just comes from the Poisson distribution where the random variable is equal to 0. And from that, you can calculate that the probability Pi, which is the probability that there are some organisms, is 1 minus the probability that there are no organisms. And you can calculate that using Poisson as well. And I refer you back to homework 1 to see where that's coming from. Then if you invert that and you isolate, and by invert that, what I mean is do what we did in the previous couple slides to isolate this. What you end up with is this here. And that actually, ta-da, that's your C log link. Where in this case, so I'm going to write that, what we had down in the previous slide, back up here. So this suggests a complementary log link where your beta 0 is your log n, your log of your original number of organisms, and beta 1 is negative log 2. Then we can use this relationship that we've just shown to estimate the original number of infective organisms, where is e to the beta 0 hat will be the original number of infective organisms, the estimated number, using a complementary log link regression model, where that's the intercept, and you also have an offset term that's equal to negative I log 2. And you can get confidence intervals by exponentiating the endpoints on the x beta scale or using the delta method. And there's a homework question related to the confidence intervals in a similar scenario, and you can either use the delta method or you can exponentiate endpoints on the x beta scale. Either way will be acceptable. So what is this offset thing? Well, offset terms are common in Poisson models, particularly Poisson regression, which we're going to cover in the next couple lectures. And they occur when the response, which in this case is the underlying number of infective organisms at step I, is proportional to some index I, which accounts for some amount of time over a spatial area or a spatial area over which the outcome is observed. And there's actually, I referenced in the beginning, Agresti has a section about this. It's like 4.5.1 or something like that, that talks a little bit more about offsets. And in this example in particular, the offset accounts for the term negative I log 2. And including an offset is equivalent to using this term as a predictor in the model and forcing its coefficient to be equal to 0. So I simulated data where the true number of infective organisms in the original sample is n equals 10,000. And the sample is then diluted 20 times, and at each dilution, it's placed on a petri dish and checked for bacterial growth, where the assumption is that there's no growth indicates that there were no organisms in that sample, and if there is growth, then it indicates that there were organisms in that sample, and that growth is recorded. So then n is the true number of infective organisms. I is the steps where sample was diluted. It can be from I to 20. I'm going to set a seed because I'm doing a simulation, so I'm going to draw some random numbers. And I'm going to put my data into a tibble that I'm calling organisms, where first you have step, that's related to that I, go from 1 to 20. Z are being drawn from a Poisson distribution with mean given by the details of this problem in earlier slides. And this is going to give you the number of organisms at each step, but this is a latent variable. We don't know the true number of organisms because we can't measure that. And we're also going to calculate this y variable, which says for each of those different petri dishes at each step, that can take on a value of 0 or 1 based on if there are any organisms in that sample. And this is what we actually do observe. just looking at that data set. So we have the step variable, we have the z's, these are counts, number of organisms in each sample. Fewer as you go further on in steps because the samples are getting more and more diluted. And then y is equal to a 1 or 0 based on whether that z value is greater than 0. So I'm going to run a C-log-log model to try to recover the true number of organisms. And in this case, I have y, the observed binary data. I'm regressing against 1 because I'm looking for an intercept, basically an intercept-only model, but I'm also including this offset term, which was -I log 2. And I'm just plug that right in like a covariate in the model, but wrapped around this offset function. And the family is binomial, but since I'm using the C-log-log link, I have to specify that here. And that's how you would specify the C-log-log model with an offset. And to actually get the number of organisms for this model, I'm going to exponentiate the intercept, and it gives me 8,100 as the estimate, which is the true value is 10,000. It's not quite there, but it's not terrible.